Good morning, grade 12s. Welcome to a glorious day. And I know you're excited to have another lesson in my class. And yeah, I'm just sort of trying to keep it to one sort of topic per week and, a little assignment and maybe a little quiz, that kind of thing. I know you get your marks on Thursday. Your quiz will be included. Like I have to go through it still. I'm not quite there yet, but I will do that today. And we basically have one topic left in this unit, and then we start the next unit. So moving right along, and this is kind of interesting. We did this before, okay, a little bit of it before, but what we haven't done is the energy part before. So I'm going to get there, and let's talk about this. Okay, so this is universal gravitational energy. So for something completely different, right? Like in the last unit, we did universal gravitation. You didn't need to draw a free body diagram or anything like that. The same thing is true here. I think you'll find this a little easier than what we've been just doing, just basically using formulas and stuff. So, all right, let's get right to it. So we're going to look at this. Here I have some nice pictures of the planets, by the way. Look at little Pluto over there, that little dot, right? Just a little tiny guy. Our moon is bigger than Pluto, right? It's a very, very tiny little guy. You can see Earth is the biggest rocky planet, and we got the gas giants, right? All right, so universal gravitation. All right, so I'm just going to remind you how it works near Earth. Okay, and then in the universe, I'll do right next to it. Okay, so near Earth, the force of gravity near the Earth, we just use mg, where g equals 9.8 meters per second squared, and that's like a broken record. We do that all the time, right? So, and this is a constant value. It doesn't vary with your distance from the Earth, right? It just varies with mass, and that number 9.8 doesn't change. We always use the same number, okay? Whether you're on the top of Mount Everest or the bottom of the lowest place you can get on the surface is like Death Valley in the United States. So, wherever you go, you get about 9.8. So we just use that as a constant. Now in the universe, if you remember from the last unit, the force of gravity is equal to a constant times the product of two masses times the distance between the centers of those masses, right? Now I assume you remember what these variables mean, but I'm just going to put down that universal constant with 6.67, really tiny number, right? Times 10 to the negative 11 Newton times meter squared per kilogram squared, okay? So that is universal gravitational force. All right, now let's talk about energy. Okay, for energy, we just did it like this. We said that the work done by gravity would equal the gravitational potential in a system, and we've been doing mgh, okay, where h is the height. Okay, that's pretty straightforward. But how do you do it for universal gravitation? All right, well, here's the deal. I'm going to move, I've got a little graph here. I'm going to move that, if it'll let me move that into the picture. Okay, so if I were to draw a graph of the force of gravity versus r, what I find is that it varies, right, with 1 over r squared. So this is like a 1 over x squared. You can ignore these numbers here. They're not important. I just used Desmos to create this graph, and it's just 1 over x squared kind of thing. But anyway, how do you find, like, say for example, you want to launch a satellite into orbit. How much energy is that going to take? Well, here's the deal. If it's a non-uniform force, let's say I start here on Earth's surface. Let's say that that value of r is the radius of the Earth. Let's just pretend, okay? And I want to get it up like 1,000 kilometers higher than that. Well, let's say that's what this number is here, okay? Actually, what I'll do is I'll just call them R1 and R2, okay? Well, how much work will I have to do, okay, against the force of gravity to elevate that object with this variable force, right? Like the force of gravity weakens with distance. So how much work will it take? Well, I'll use my little rainbow color here. We've seen variable forces before, and the work required, okay, will equal the work done against gravity will equal the area in a force versus distance graph. Remember how work is like product of force and displacement? Well, if you have a force and displacement graph, okay, the work done is equal to the area underneath the line, and that's especially useful if the force is not uniform like this, okay? Now, you guys are calculus experts, of course, so what I want to do is, we're not going to just estimate how much area is there. You're never going to have to do calculus in this class, but look, I just want to give you an example from calculus, okay? And it's kind of cool because you know some calculus now. I could never do this in grade 11, but now you know a little bit. Let's say I have y equals 1 over x squared, okay? Now, here's the deal. When you're finding the slope on a line, you take the derivative. But when you're finding the area under the curve, you take the reverse derivative, or what we call the antiderivative, and sometimes it's called the integral, okay? So the area, what I would like you to know, is the area here is equal to the antiderivative, okay, of the gravity function. Now, because it's a 1 over r squared function, we're going to use 1 over x squared from calculus. Now, if I were to ask you this question in class, what function would you start with so that its derivative would equal 1 over x squared? Well, watch this. If I just say, like, what I want to find is a function that, here, let me say it like this. If this is 1, this is x to the negative 2, okay? So there is a function that exists so that its derivative is equal to x to the negative 2. In other words, like, what is the antiderivative of this function? And the answer would be, okay, if y equals negative 1 over x, okay, which is equal to negative x to the negative 1, if I take the derivative of this function, I get 1 over x squared, okay? And that's what this one is. So therefore, the antiderivative, the area under the curve, okay, would equal, now what you do is you write the antiderivative like this. Now this is going to look very confusing. This is actually called taking the area. But what you do is it's equal to, we write it like this, and you're going to evaluate it between R1 and R2, right? Find that like fixed area there. And you get negative 1 over x is the antiderivative, but we evaluate it between R1 and R2, okay? And so it goes like this. You get 1 over R1 minus 1 over R2. Turns out to be the antiderivative. So the area underneath this line, okay? So this area, that's what it's equal to. And you get it from calculus. Now, please, like, if you thought this was very confusing and you don't get it, that's fine. I'm never going to ask you to derive the formula. But it's cool to see where it comes from. And since you know a little bit of calculus, if you can do the derivative, okay, of this function here, then the antiderivative of that, okay, sorry, the derivative of this function is this function. Therefore, the antiderivative function of this guy is equal to this one, okay? So anyway, derivatives and antiderivatives. So if you know how to do the derivative, the antiderivative should make some kind of sense. You just sort of use the rule in reverse, right? Now there's more to the story that I'm not quite filling in all the details for you how you get to this equation here. But let's just suffice to say that there's a way to find the area underneath a curve that is not by guesstimating or estimating, right? So this area here, okay, is equal to this. So that's kind of cool. Now we're going to use that, okay? So when we do universal gravitation, I'm going to use a little rainbow divider here. It's so simple, right? When we're doing it near the Earth, just MGH, that's it. But here, okay, with this universal gravitation thing, we have to say the work done by gravity equals the gravitational potential is the area here under the line, and that turns out to equal G m1, m2, these are constants, and then it's going to be times 1 over r1 minus 1 over r2. Okay, now this is how you do universal gravitation with universal gravitation, like so energy, universal gravitational energy, this is how you do its gravitational potential, or the change in gravitational potential. Okay, it's as simple as that. Okay, so there you go. That is a new formula for you. And it's unfortunately, that's not the end of the lesson. There's a couple of other things we have to discuss. Okay, it's so funny though, because that's the end of our little table for near the Earth. It's so simple, right? But in the universe, not so much, okay? Like it's a little bit more complicated. That's okay. We just use this formula and we'll get it, right? Okay, now there's a couple other things before we move on to doing some problems that I'd like to discuss. This is how you do universal gravitational energy when an object is moving from R1 to R2. How much energy that will require is given by this formula, okay? However, so if you want to launch a satellite into space, for example, you need to use this formula. The MGH, not going to work, okay? It's too far. And when it's too far, we have to use universal gravitation. Okay, so this is like formula number 1, if you like. Okay, so now what I'm going to do is I'm just going to summarize down here. Universal gravitation. I'm just going to start sort of a new note here with it. I'm going to say 1, the force of gravity is equal to G m1 m2 over r squared. 2, the gravitational potential energy is equal to G m1 m2 times 1 over r1 minus 1 over r2, like this. Okay, and now I'm going to add some notes, okay? All right, so let's talk about something called binding energy. Okay, binding energy. Let's say, for example, that you are bound to the Earth right now. Okay, what binds you to the Earth is gravity. Everything is bound. Everything you look around the room where you're sitting right now. Everything you see is bound to the Earth by gravity. It can't just float away, at least not very easily. Okay, now let's say you could throw a ball up in the air. Well, is it possible that you could unbind an object from the Earth? Like, could you give it a kick, and a kick that's so hard that it will never return? Okay, so the answer to that question is yes, of course. We've sent many things out there into space that will never return. I'm not talking about the orbiting satellites. They are still bound to the Earth, right? The space station is still bound to the Earth. That's why it orbits the Earth. However, you can send something to Mars and unbind it from this Earth, okay? Now, what we do is we take this formula. If R2 approaches, the universe is a big place. Now, it's not infinitely big, but let's say we were to get something so far away that it's like a trillion miles away from Earth, okay? Well, if you look at the formula for gravitational energy, the energy, if you remember limits in calculus, will approach G m1 m2, and then I'm going to write the formula again, 1 over r1 minus 1 over r2, like this. Well, that one there is going to approach 0. Okay, if R2 approaches infinity, in other words, if you're launching something so far away, that's such a big number, then that 1 over that big number is going to approach 0. And so you just get this. Therefore, the binding energy, this is the amount of energy it's going to take so that you get something that far away, is going to be G m1 m2 over r1. And so this is called the binding energy, right? So how much energy would it take to get something loose of gravity, to make it escape Earth completely, okay? Now, there's something that's connected to this called escape velocity. Okay? Escape velocity is how much speed you need, okay? So like let's say we'll do an example for Earth in a moment, but how much speed would it take to escape the Earth, right? So this is equal to the velocity required to escape a gravitational field. Okay, so you want to escape Earth. Well, it's obviously connected to binding energy, but what you're going to do is just give something enough kinetic energy that it's equal to its binding energy. So therefore 1/2 m1v squared equals g m1 m2 over r1. m1, by the way, is the escaping object. m2 is usually a planet, etc., not the thing that's escaping the planet. Anyway, m1 cancels. So whether you weigh 50 kilograms or 100 kilograms, it doesn't matter. You're going to have the same escape velocity. Not the same binding energy, because that does depend on your mass, but the same escape velocity, right? Because that your mass, or the satellite's mass, or the space station's mass, cancels out. Okay? m2 would be Earth's mass in this case. Okay? So anyway, I'm going to solve this for speed. You get speed equals 2g m2 over r1 square root. Okay? So this is your escape velocity. Isn't that cool? Your escape velocity. Okay, so let's do some examples, and let's take our favorite planet as our example, and of course our favorite planet is our home. So let's do some examples. Okay, and I'm going to give you an example of how to use all three of these equations, and then that's it for the lesson for today. So, and then I have actually a very short assignment, much easier than the one you got last week. And I was thinking maybe we could have like a really quick quiz on this if you want. Maybe we could do it sooner rather than later and give you a chance to boost your mark again before I put in your marks on Thursday. It's up to you though, I don't want to stress you out. So, all right, so look, let's do some examples. All right, first, let's do Earth. It really doesn't matter what planet you're on though, as long as you have the mass and radius, you're good. So Earth has a mass of 6.0 times 10 to the 24 kilograms. Okay, and its radius is 6.38 times 10 to the 6 meter. Okay, so now let's say you're standing on Earth's surface, which you are. Okay, doesn't matter if you're upstairs or downstairs, that small difference in distance from you and the center of the Earth doesn't really make much difference. You're about 6.38 million meters from the center of the Earth, so a couple more meters won't make much difference if you climb a hill or something. However, okay, let's say you want to escape Earth. So you build your spaceship and you want to escape. Okay, but before you escape, maybe you want to make it into the space station like orbit zone, somewhere around there. So let's say you're going to start at the radius of the Earth on the surface. So you're starting on the surface. Okay, and then R2, let's say you want to go up 1,000 kilometers. Okay, so my question for you is, how much energy will that take? How much energy, gravitational energy, you're going to be fighting gravitational energy, so how much gravitational potential will you gain when you do this? Well, so this is question A. Okay, so in question A, we're going to use the first formula, Eg equals G m1 m2 times 1 over r1 minus 1 over r2. Okay, now you have to be good with your calculator on these questions, right? So, and you will need a calculator, so I'm going to do it for you right now. So I'm going to go, first I'm going to do what's in the brackets. So R1 is 6.38 times 10 to the 6. And before I do R2, just a little note here. You have to add the radius of the Earth. I made a mistake here. We're going to go 100 kilometers, an altitude of 100 kilometers above the surface. So I need to convert that. That's 1 times 10 to the 6, 1,000 kilometers. So that's going to be 7.38 times 10 to the 6 meters. So that's what R2 is. Okay. All right. So I start with R1, 6.38 exponent 6. And I use the 1 over x button in my calculator. It looks like this, 1 over x. I suggest you do the same, and then we go minus 7.38 exponent 6, 1 over x. All right, so I got a number in brackets, times 6.67. Times, let's say your mass, I got to put your mass in here. Let's say M1 is 50 kilograms. So times your mass times Earth's mass, 6 exponent 24. And I get 4.25 times 10 to the 8 joules. So 4.25 times 10 to the 8 joules. Now, just out of curiosity, okay, if you were going to do it the old-fashioned way, I'm going to say, what about good old-fashioned MGH? Okay, here, I'll write it over here. EG equals MGH. What about that? Would that have given us the same answer? Well, your mass is 50, G is 9.8, and it's 1,000 kilometers, so that's 1 times 10 to the 6. So if I do that, I'm most certainly going to get a larger number. 50 times 9.8 times 1 exponent 6. And I get 4.9 times 10 to the 8 joules. And this number here, that number is definitely wrong. Okay? See how it's much bigger than this number here. It's 4.9 instead of 4.25. The reason why it's wrong is because it's not factoring in the fact that gravity gets weaker with distance. It's not just going to be 9.8 if you go 1,000 kilometers away from Earth's surface. Like, not even close. Okay, so just keep that in mind. When we're going into space, you have no choice. You have to use universal gravitation. All right, so that's example A. No problem, right? Just using a formula, no free body diagram. It's all good. All right, question B. What is the binding energy, okay, of this object, this 50 kilogram object? Okay, so you are 50 kilograms and you're on Earth's surface. So what is your binding energy? Well, let's find out. The binding energy, G M1 M2 over R1. We don't need R2 this time because R2 is basically infinity when you're doing binding energy, so it's just the first term. So 6.67 exponent 11 negative times 6 exponent 24 times 50 equals divided by, oh, I'm sorry, this is an R1, divided by 6.38 exponent 6. And I get 3.12 times 10 to the 9 joules. So 3.12 times 10 to the 9 joules. Now, is that a lot? Well, I mean, here, to give you some perspective, it's definitely doable. Of course, we can do this with modern technology. That's about like 871 kilowatt hours worth of energy. Now, if you know anything about electricity, my solar panels on a beautiful sunny day like this produce about 80 kilowatt hours a day. So in about 11 days, if I stored the energy in my solar panel, I'd have enough to launch you away from Earth and you'd never come back, right? Now that's just for a 50 kilogram mass, but let's say it's a 50 kilogram satellite. Now, of course, in reality, it takes a lot more energy than that because we have this annoying problem called air resistance when you're launching something very fast up into the atmosphere. Okay, and that is going to change things a lot. It's going to, actually, that is going to add a tremendous amount of energy to our launch. That's why it's so expensive to get things into space. All right, what about your escape velocity? What is your escape velocity? Okay, well, to do your escape velocity, you're just going to do this. 1/2 m1 v squared equals, actually, why don't we just, since we already derived this formula, it's right here, 2g m2 over r1. So V equals 2G M2 over R1, like that, square root. Okay, you would expect this for you to escape Earth for it to be a very high number, right? 2 times 6.6 negative times 6 exponent 24 divided by 6.38 exponent 6, and then take the square root. I get 11,201 meters per second. Now that is around Mach 33, which means 33 times the speed of sound. But guess what? Orbiting satellites and stuff like that, they're going pretty close to that speed already. They're not quite enough to escape, but that's how much speed it takes. That's Earth's magic number. Any mass on our surface, if you give it this much speed, it'll leave and never come back. Now, that's a lot of speed. That's not easy to do. Okay, but it can be done. Okay, not all at once. We got to get it accelerating and stuff like that. And air resistance guarantees that that number is going to be even higher than that. But anyway, that's how much speed you need to escape Earth's gravity. Okay, if you were to go to a planet without an atmosphere, that would be the exact number. Okay, so that's escape velocity. Now, I want to talk about one more thing, orbit problems, because this is going to come up on the short assignment I have for you. So when you're orbiting, we know the free body diagram of an object in orbit looks like this. There's gravity. Let's say this is your planet down here. There's acceleration. It's radial acceleration. You know, the object is moving that way with some speed v. Okay, so this is a centripetal. There's only gravity, right? So it's a centripetal motion problem, and we know that MAR will equal G M1 M2 over R squared, the force of gravity. Now this M1 is the mass of the satellite. Okay, actually, you know what? I'm not going to cancel it. I'm going to leave that in there for a second. Okay. So what about, what do we put in for AR? Well, we go like this, mv squared over r, little r in this case, equals g m1 m2 over r squared. Okay, now one of those can cancel, okay, with one of those. And what we're left with is this, okay, that mv squared, this is m1, I keep forgetting to put that in, equals g m1 m2 over r. Now, if you look at that, that is looking like the binding energy, isn't it? Like, it's kind of interesting how that works out. But I'm just going to say that EK equals 1/2 m1 v squared, right? So this is kinetic energy for orbit. Now, all I need to do is introduce a factor of 1/2 on both sides, and then therefore 1/2 m1 v squared is equal to g m1 m2, and I have to put the half on this side, so that's going to show up like this. So it's like half of the binding energy, right? Anyway, this is the EK required for orbit. Okay, now that's kinetic energy required for orbit for an orbiting satellite. Okay, whatever that satellite is. Now what I'm going to do is I'm just going to go, therefore the launching something in orbit, this is what you would do. On the surface of the planet, okay, you would give, this is at R1, what you would start with is EK, okay? And then you're going to give it in orbit, okay? The orbital energy will equal the change in gravitational potential plus the EK for orbit that we just worked out right there. Okay, so that's going to equal g m1 m2 times 1 over r1 minus 1 over r2, and then you're going to add g m1 m2 over 2 r2. okay? R2 being the orbital radius, okay? Now there are like terms here, but I'm just going to simplify it for you. I don't want to waste your time with doing this kind of algebra that I'm never going to ask you to do. I'm just going to give you the formula. So I'm going to group the like terms, G, M1, M2. You're going to get 1 over R1 minus 1 over 2 R2 is what it works out to. Okay, now I'm going to put a little box around this. So this is when you're launching to orbit. Okay, so when you're launching to orbit something, you use this formula here. And what you're going to do is you're going to replace this equation here with 1/2 mv squared, where v is the velocity of launch. So if you're asked for a launch velocity to get something into orbit, that's how you do it. Now it's kind of cool how it works. If you think about it, if you want to launch something into orbit, you have to give it a launch energy that's basically equivalent to the amount of shooting it straight up, so it goes twice as far away as you would really want. But you see, when it gets to orbit, it has to have some kinetic energy to stay in orbit, right? So this little formula here will save you some time, but it's only specifically for launching things into orbit. All right, so now that we've done like several examples, that's really the whole lesson. I wanted to show you there's a little worksheet. There's not much to it. There's only 3 questions here, but some of them have A, B, and C, and so on. And so here's the deal. I included some planetary data for you here, okay? And so like if you look at the first question, what's the minimum speed relative to the sun necessary for a spacecraft to escape the solar system if it starts at Earth's orbit, okay? Now, I'm going to change this later. I'm going to add the orbit distances from the sun for you, okay? So you need that distance. And of course, in that equation, what you're going to do is do escape velocity. So V will equal G M1, or M2, sorry. Let me do this. 2G M2 over R square root. And R will equal Earth's orbital radius, which is 1.5, I think, times 10 to the 8 meters, I think. Let me verify that number. You know what, I'm going to erase it for now, not to confuse you. It's either 1.5 times 10 to the 11 or 1.5 times 10 to the 8, I forget the number. So I'll just look it up and put it in there for you. And I'll update this worksheet with the orbital radius numbers that you need, okay? But anyway, that's how you do it. See, you just use a formula. Piece of cake, okay? And I'll let you give this a chance here, or give it a try. It shouldn't take very long. It should take maybe less than an hour to do it. And that is our work this week. All right, guys, so I'm going to end it there. That is it for universal gravitation. And that's our last topic in this unit, by the way. And I think the course gets easier from here on out. So I hope you agree with me. Starting with this isn't too bad, just using formula. All right, so have a good day, guys. Enjoy this beautiful weather.